All right, our second day continues with Jesse's lecture.
Okay, great. Yeah, so thank you all for coming back. So yeah, this is the second lecture on minimal submanifolds and spheres. And unlike the last lecture where we talked about generalities about minimal submanifolds and didn't really focus on the sphere part, in this part we will actually study minimal submanifolds and spheres. This lecture is maybe a bit non-standard in certain respects. First of all, it might run a bit short. In a sense, I don't have that much to say. The main thing is more that I want to advertise a certain style of thinking. There's a very particular philosophy that I think is very useful in formulating problems and sort of organizing the otherwise, the chaos that is high codimension minimal submanifolds and spheres. So really, there's no sort of main theorem that this talk is building up to. This is not a traditional research talk. What this is meant to advertise really a collection of problems and a way of thinking about them. And really, this is meant more of an advertisement for future work than anything else. This lecture grew out of, I originally intended to write a survey article on this lecture, and I suppose maybe this will motivate me to do it. So sorry about that. So yeah, just recall that the structure of these lectures is like this. Lecture 2, this one depends on the previous one, but if you don't like this lecture, that's okay. The next lecture, lecture 3, won't depend on this, so you don't need to memorize everything on in this lecture, I suppose. Yeah, so we're going to talk about semi-calibrated submanifolds and spheres, and I'm going to focus on 3 out of the 4 cases of interest, which are the 6-sphere, odd dimensional spheres, dimension 2n+1, and then those spheres whose dimension is 3 more than a multiple of 4. Notice the dimension restrictions. We will always be working in spheres that are dimension 5 and higher. Okay, there's a bunch of preliminaries I need to explain before we get started. Right, so first of all, why would you study minimal submanifolds and spheres? One motivation is just that spheres are a very natural Riemannian manifold, of course. But the other motivation, even if you don't care about spheres, even if you only care about Euclidean space, the fact is that minimal submanifolds and spheres are relevant to the study of minimal submanifolds in Euclidean space because minimal submanifolds and spheres model conical singularities. So let me make that precise. So we're going to think of the n plus k sphere throughout this talk as the unit sphere in R n plus k plus 1. And we'll let sigma n be an n-dimensional submanifold. For now, n is at least 2 and k is at least 1. Yeah, n and k are at least those numbers. So given such a submanifold sigma, we can define the cone over it. Okay, so the cone over sigma is the n+1 dimensional submanifold defined like so. You just take sigma and you just scale it by r. Okay, and in this context, we refer to sigma itself as the link of the cone. So in a sense, we view somehow the link sigma and the cone, they sort of go back and forth. Sometimes we focus on the cone and other times we focus on the link. The point here is this is a sort of standard computation that the cone is minimal if and only if the link is minimal. So it is in this sense that minimal submanifolds of spheres model conical singularities of minimal submanifolds in Euclidean space. I must emphasize that the cone could be stable. The cone could even be area minimizing. That happens, that'll be sort of the focus of this talk, but the link never is, right? So the link is never stable, the link is never area minimizing, but the cone may or may not be. It's a very interesting question to ask, if you know the link, is the cone stable? Is the cone minimizing? How can you tell? This is a very interesting, non-trivial question, but that's not, and I'll talk about it maybe again briefly in the next lecture, but only briefly. That's not the focus of today. One construction we'll need briefly, only briefly, is the sine cone construction, which I sort of wish were more widely known. So let sigma be an n-dimensional submanifold of the n plus k sphere. And I want to think of the n plus k sphere now as the equator in the n plus k plus 1 sphere. Now, okay, I can parameterize the n plus k plus 1 sphere in the following funny way. I can think of the points as pairs sine theta p comma cos theta. Okay, and theta is in 0 pi. So what you should imagine is that theta equals 0 gives you the North Pole, theta equals pi gives you the South Pole, and then theta equals pi over 2 gives you the equator. So using this parameterization, I can talk about the sine cone of sigma. So I can take sigma and I can form its sine cone. It's defined by basically the same formula, but now I only restrict, now the points P have to live in sigma. So so sigma was n-dimensional. Its sine cone is n plus 1 dimensional. So what this did was I took sigma, which lived in the equator, and I got a submanifold 1 dimension higher in the sphere 1 dimension higher. Okay, so this is actually a very canonical construction, and it shows up a lot for the following reason. It turns out that the cone over the sine cone is in fact equal to the cone times r. Okay, you can convince yourself of this by writing things out in the appropriate coordinates. It's kind of a funny fact that the cone cross r is itself a cone, and it's precisely the cone over the sine cone. So this diagram commutes. And again, I should emphasize that in general, the sine cone will be singular. In a sense, these are arguably the simplest singular minimal submanifolds in spheres. And I think increasingly these will be of a lot of interest because increasingly folks are interested in not just conical singularities, but conical singularities where the link itself is singular. And the simplest situation of that is what you see here. Okay. All right, so the other preliminary notion we need is that of a semi-calibration. So in general, if M is a Riemannian manifold, for us that Riemannian manifold will be a sphere, a round sphere. But in general, if M is a Riemannian manifold, a semi-calibration is just a differential form of comass 1. Okay, so at each point, the maximum value that your form can take on orthonormal sets is 1. Okay, so a calibration, which we talked about last time, a calibration is just a semi-calibration that's closed. Right, so a semi-calibration is somehow just 1/2 the definition of a calibration. So notice that already with the definition of semi-calibration, we can talk about what it means for an oriented submanifold to be semi-calibrated, right? So it's the same exact definition as in the previous lecture. If I have an oriented submanifold sigma of dimension n, which is the same degree as the form phi, I can say that sigma is semi-calibrated by phi if phi restricts on sigma to be the volume form of sigma. Okay, you say it's calibrated, of course, if phi is a calibration. Okay, now from the fundamental theorem of calibrations that we talked about last time, calibrated submanifolds are area minimizing. Oh, there's something in the chat, sorry. Oh, never mind. Okay. Anyway, yeah, so by the fundamental theorem of calibrations, every phi calibrated submanifold is area minimizing, and in particular, they're stable, and in particular, they're minimal. This is not the case for semi-calibrated submanifolds. In general, semi-calibrated submanifolds don't have to be minimal. Semi-calibrated submanifolds in general, there's sort of, perhaps not much you can say. It's not really clear. But sometimes there are certain semi-calibrations, which I'm going to call nice, for lack of a better word. There's no standard word for this as far as I'm aware. A semi-calibration will be called nice if every semi-calibrated submanifold is minimal. Okay, so the nice semi-calibrations form a subclass of the semi-calibrations, and that subclass includes all the actual honest calibrations. Okay, so semi-calibration phi is nice if all semi-calibrated submanifolds are minimal. And the point I'm going to make in this lecture is that nice semi-calibrations are maybe, they show up in spheres quite a lot. They're maybe more abundant than maybe is, commonly reported. Okay, so what is the sort of overarching story of this talk? Remember that every minimal submanifold in the round sphere is unstable by Simon's theorem. In particular, minimal submanifolds of spheres are not calibrated, because calibrated submanifolds would be stable. And moreover, the index is at least 1. So a problem that motivates us throughout the entire lecture series is this: given a compact, given a compact minimal submanifold in the sphere, calculate its Morse index. In general, when I say hard, I mean this is just impossible. In the vast majority of cases, calculating this number is not feasible, like, at all. Okay, except maybe this is tractable when sigma is sufficiently simple. So maybe in the simplest possible cases, we can do this. This raises the question of which minimal submanifolds are simple. And here I'm not just talking about hypersurfaces, codimension 1, I'm talking about any possible codimension. Sort of how can we impose order on the chaos that is sort of the giant class of all minimal submanifolds of any codimension. So I want to argue that there are sort of 2 natural conditions that you can put on a minimal submanifold that make it simple. So one is you can require symmetry, right? So homogeneous minimal submanifolds, those that are G orbits, where G is a subgroup of SO n plus k plus 1, and G acts linearly on the ambient Euclidean space. G acts transitively on sigma. Okay, these submanifolds, for these submanifolds, it's maybe more feasible to calculate the Morse index. Even for these submanifolds, calculating the Morse index is extremely hard and may not be really doable, but at least there's maybe some hope. The other class, which sort of will take center stage in this talk, are those that are phi semi-calibrated, where phi is some nice semi-calibration. One nice feature of nice semi-calibrations is that the following often happens. For virtually all the examples that I know, or at least all the examples that will arise in this talk anyway, you can actually factor the Jacobi operator. So when you have a phi semi-calibrated submanifold and phi is nice, not always, but I don't think, but often you can find a Dirac operator on the normal bundle and some constants such that the Jacobi operator can be written as a quadratic in the Dirac operator. And so that's essentially, it reduces this somehow, this second order problem to a first order problem. And it also gives you a more geometric way of thinking about the various Jacobi eigenspaces. Sort of oftentimes this Dirac operator, it's tied to the geometry of the semi-calibration. So somehow, if there's a geometric meaning to the semi-calibration, then there's a geometric meaning to the Dirac operator. And this gives you, well, just simply more geometric things to work with when it comes time to playing around with the various eigenspaces of the Jacobi operator. This is something which often happens. I'll illustrate this briefly later. Okay, so here I am talking about spheres admitting semi-calibrations, but like are there any semi-calibrations? Where do they come from? Are there some canonical examples? And sort of the answer is yes. And the vague principle here is that if you have some calibration that's canonical on Euclidean space, then that often induces a canonical nice semi-calibration on the unit sphere. Yeah, probably this can be made precise. Probably there's some theorem or proposition or lemma or something one can prove to this effect. I haven't tried. Or well, I tried at one point and it was sort of too annoying, but maybe one of you can work this out. Okay, but the point is that in the last lecture, at the end of last lecture, we talked about various calibrations on Euclidean space, and the upshot is that those induce nice semi-calibrations on spheres. Here they are. So this table is quite formidable, so let's talk about it. So these will be familiar from Berger's list, right? So the right side of this table is maybe familiar. So here we have R2n plus 2, where you can think of it as Cn plus 1. And in Cn plus 1, we have 2 types of sort of very natural classes of calibrated geometries, the complex submanifolds and the special Lagrangians. Okay, and if we think of these as cones, then they have links. And it turns out that their links are semi-calibrated, and they're semi-calibrated by a nice semi-calibration. The semi-calibrated links are called CR and special Legendrian, respectively. Similarly, in HN+1, there's the complex Lagrangians, for example. There's also complex and special Lagrangians again, and just millions of others. The quaternionic case, this case is by far the most complicated. I'll return to this at the end of the talk. And in particular, you get a class of semi-calibrated submanifolds of the 4n+3 sphere called CR Legendrians. In R7, we have associatives and co-associatives. These can be cones. Their links are called holomorphic curves and Lagrangians in S6. And in R8, you can have Cayley cones. Their links are called associatives. Again, all of these are defined by first order PDE. Okay, all of these submanifolds in this column are necessarily unstable minimal submanifolds. They're all minimal submanifolds of spheres. Okay, and I would argue that in a certain sense, these are simpler than taking just a generic minimal submanifold in a sphere. That these are maybe more tractable, at least in high codimension to study, because they have extra structure. And they're also interesting from the point of view of special geometry. Okay, so let me illustrate, for example, the case of S6. So I want to think of R7 as the imaginary octonions. Recall from last time that there are two G2 invariant differential forms that we can study. There's the associative 3 form, defined like that, and the co-associative 4 form is its Hodge star. We're thinking of S6 as the unit sphere, and using this 7-dimensional cross product, which we talked about last time, we can define an endomorphism of the tangent space of the 6th sphere, like so. Jp of V is P cross V. The properties of this 7-dimensional cross product are such that this ends up being an almost complex structure. So J squares to -1. Moreover, it's compatible with the round metric. So J acts as, I should have written this on the slide, but J acts by isometries with respect to the round metric. Okay, so let R be the radial coordinate on R7. We can write the 3 form phi in this form, it turns out, and we can write the 4 form like that. And here beta is a non-degenerate 2 form, and gamma is a nowhere vanishing 3 form. It turns out that beta is essentially I hesitate to call it a Kähler form, it's not closed, but it is essentially the Kähler form corresponding to the round metric in J. So it's a type 1-1 non-degenerate form. And gamma is sort of like a special Lagrangian form, so to speak. Right, but of course it's not parallel. Okay, so the point is that beta and gamma, which live on the 6th sphere, are very fundamental to the geometry, not just of the 6th sphere itself, but to the geometry of natural submanifolds. So for example, we can say that a surface, sigma, 2-dimensional in S6 is a holomorphic curve if each of the tangent spaces are J invariant. This is equivalent, it turns out, to requiring that sigma be semi-calibrated by beta, and this in turn is equivalent to requiring that the cone be associative. Okay, probably I'm being a bit sloppy with regards to orientations. Okay, so even though beta is not a calibration, it's a semi-calibration, and moreover, it's a nice semi-calibration. Right, I mean, this chain of equivalences shows that every holomorphic curve is a minimal surface, right? Because if I have a holomorphic curve, its cone is associative, therefore the cone is minimal. But if the cone is minimal, then the link must be minimal. So that shows that beta is a nice semi-calibration. Similarly, we can talk about Lagrangians. Remember, beta is like a Kähler form. It's a non-degenerate 1-1 form that arises in the normal way, in the usual way. It's just not closed. So a 3-dimensional submanifold of the 6th sphere is called Lagrangian if beta vanishes on it. Interestingly, because S6 is not, it's really far from being Kähler. It's so far from being Kähler, it's called nearly Kähler. Kind of a strange name. Beta vanishing actually implies that gamma vanishes as well, which is sort of unusual. And that turns out to be equivalent to requiring that L is semi-calibrated by negative of the Hodge star of gamma, and that's equivalent to requiring that the cone be co-associative. So the upshot is that the Hodge star of gamma is in fact a nice semi-calibration again. And so Lagrangians in S6 are automatically minimal, right? This is sort of in stark contrast with how Lagrangians work in a Kähler manifold, for example, right? Lagrangians and Kähler manifolds need not be minimal. This is sort of a funny feature of, nearly Kähler manifolds. Okay, so these are sort of the two natural, I would say the two natural classes of the sixth sphere, two natural classes of minimal submanifolds of the sixth sphere. So, it would be nice to understand their Morse index. And this, of course, is a hard thing. But maybe you could start by calculating the Morse index for the homogeneous examples. So what are the homogeneous holomorphic curves, for example? If you combine results of Calabi, Kenmatsu, and Sekigawa, you get the following. Suppose sigma is a compact holomorphic curve in the sixth sphere. It turns out that there's only 3 homogeneous examples of such. There's the equator, which has Gauss curvature 1. There's what's called the equilateral torus, which lives in the 5 sphere, in the equatorial 5 sphere. Sometimes I guess that's the Clifford torus in S5. That has Gauss curvature 0. It's a flat torus. And then there's the Boruvka sphere. The Boruvka sphere was discovered some like 90 years ago by Boruvka. It's an orbit of the irreducible SO3 action on R7. So it's defined by sort of these harmonic homogeneous cubic polynomials. So it's some sort of cubic sort of object. It's not the most pleasant thing to write down, but you can write it down explicitly with polynomials. So these are the simplest holomorphic curves. It would be good to know their Morse index. The equator has index 4 by an old result of Jim Simons. The equilateral torus, this is my notation for this one, of course, has Morse index 9. And the Boruvka sphere, it's actually not clear what the index is. I'm currently working on that. It's known that whatever the index is, it's at least 36. But it would be nice to know the actual number. And again, if you think of the Morse index as some sort of measure of complexity, you might be tempted to conjecture that somehow, like among all holomorphic curves, these numbers are perhaps the lowest that can occur for the Morse index of compact holomorphic curves in S6. That's, I think, a reasonable thing to guess. I don't know whether that's true, but that's the kind of thing that maybe one would hope to investigate. One can similarly talk about the Lagrangians in S6. The homogeneous ones are again classified. Here the classification is a bit richer. Other than the equator, there's this Veronese RP3. Okay, this RP3 again lives in an S5. We'll come back to it later. There's the S3, which is given by the link of the Lawson-Osserman cone, which was referenced last lecture. The Lawson-Osserman cone, in fact, was co-associative. I failed to mention that. And therefore, its link in S6 is Lagrangian. Right? This is this famous example that was a counterexample to many, hopes about high codimension and high dimension minimal submanifolds. And then there's 2 examples with some interesting topologies, S3 mod these various finite groups. So the equatorial 3 sphere has index 3. The other 4, I don't know what their Morse index is. I've never seen it written down. As far as I can tell, there's a paper of Jason Lotte in which he studies not these submanifolds exactly, but he studies their cones. And he gets some very detailed, very precise calculations. And I'm fairly sure that from those calculations, you can extract the Morse index in a fairly straightforward fashion. I haven't done this. I'd be very curious if anyone wants to do that, to tell me what exactly the Morse indices of these 4 are. I'd be quite curious, but I think this is very straightforward from the calculations that he has in that paper. Okay, yeah, so I just sort of want to return to this point that I briefly mentioned, and I'm only going to briefly mention again earlier. So if I have a compact holomorphic curve in S6, then it turns out that using the cross product on the ambient R7, one can write down this natural Dirac operator on the normal bundle. I won't explain this, what this is, but the result is that the Jacobi operator factors like this. So for example, what this tells you is that the nullity which is, or really the, you know, the variations in the null space of the Jacobi operator really come in two types. There's the type for which this is 0, and then there's the type for which this is 0. So kind of the eigenspaces of the Jacobi operator split into these two pieces. Oh, is there any relation between this Lagrangian and Lagrangians in physics? Not in the way that you mean, I don't think. I mean, there's, what is there? I mean, here, I mean Lagrangian in the sense of symplectic geometry. I mean Lagrangian submanifolds, and Lagrangian submanifolds are certainly related to physics. They're relevant to classical mechanics, but that's different from the Lagrangian of an action, I think. I'm not a physicist, but Lagrangian submanifolds are certainly relevant to you know, classical mechanics, well, the Lagrangian and Hamiltonian formulations. Anyway, yeah, so the point is you can factor the Jacobi operator of a compact holomorphic curve like this. See, for example, this paper of Goropada-Berra. And you can get more geometric information about the Jacobi eigenspaces.
There is a question that maybe.
Oh,
yeah.
I think I just answered it.
Oh, okay.
Yeah, I think I just answered that. Yeah, yeah, physics. Let's see. And yeah, so for Lagrangians in S6, you can do a similar thing. I won't write it down, but it turns out that for Lagrangians, the situation is even better because the normal bundle ends up being intrinsic, right? That's one of these, you know, miracles of Lagrangians. The normal bundle is isomorphic to the tangent bundle, which is isomorphic to the one forms, which allows you to use Hodge theory. This was written down quite some time ago by Bennett Palmer, and you know, certainly this is used in the study of co-associative cones, but I expect that you can get quite a bit of mileage out of this type of thing if one was interested in the Jacobi operator or the index of Lagrangians in S6. Okay, so it might seem as though everything I just said about S6 was somehow very special. And in a sense, that's true, in the sense that, you know, we use the octonians, and, you know, there's only one number system, that's the octonians. But in other respects, a lot of what I said sort of carries over to sort of all odd dimensional spheres, at least formally. So let's talk about odd dimensional spheres. So now I want to think of my ambient space R2n plus 2 as Cn plus 1. There's a standard complex structure J on this ambient space. I'm going to let omega be the Kähler form and upsilon be the complex volume form from last time. So this data, so all of this data on R2n plus 2 induces quite a bit of information on the 2n plus 1 sphere. So first of all, we get a contact 1 form, and we get a Reeb vector field. Okay, so the contact 1 form I'm calling alpha, and the Reeb field I'm calling psi. So psi is nothing more than the tangent vector field to the Hopf S1 action. That's the ordinary S1 action given by multiplying by e to the I theta. And here R is the radial coordinate, of course. And so the result is that we have this orthogonal splitting. You know, the tangent space to the 2n plus 1 sphere can be split as sort of this, there's this Reeb field direction, and on the other hand, there's this orthogonal 2n plane. And this, I think, is sort of the way, you know, this is a very good way to think about the geometry of the 2n plus 1 sphere is in terms of this decomposition. Moreover, there's this endomorphism as well on the tangent spaces. What you do is you just take J on D. D is a 2n plane, and then you just extend by 0 to the Reeb line. And finally, you have this complex N form here, and it's just obtained from the complex volume form on R2n plus 2, and you can do sort of the same game that you did with alpha. The result is all of these tensors, you have the round metric, alpha, math frac J, and psi, and all of this comprises a Sasaki-Einstein structure. This is the standard Sasaki-Einstein structure on the 2n plus 1 sphere. So here's that data summarized again. And so now that you have all these fun tensors, you can start defining some relevant classes of submanifolds. Oh, and one more thing. Each 2n plane has a Hermitian structure, right? It's not structureless. It has this Hermitian structure, as you might expect from sort of working through the Lie groups. The Hermitian structure is given by the round metric, J and sigma. Sigma is, I guess, the 1, 1 form, if you like, the Kähler form again, given like so. And you can calculate that d alpha is 2 sigma, at least in my convention. So here's our first class of submanifolds of odd dimensional spheres. We'll say that an odd dimensional submanifold of an odd dimensional sphere is CR if its cone is complex. Okay, so it's necessarily odd dimensional, and we say that it's CR if its cone is complex. And it turns out that such submanifolds are semi-calibrated by a very particular semi-calibration. It's this one, 1 over k factorial times alpha wedge sigma to the power k. Sigma is defined over here. And that's equivalent to requiring that the tangent space be J invariant and that it contains the read line. So sort of on a linear level, you can understand it very well. And again, these 2k plus 1 forms are nice semi-calibrations. Every CR submanifold is minimal. I mean, in my opinion, these are extremely fundamental. They're the links of complex cones. It would be really great, I think, to understand the Morse index of these things in greater detail. The other class of submanifolds you can talk about are, of course, the special Legendrians, right? If you have complex cones, you can talk about their links. You have special Lagrangian cones, you can talk about their links. So an n-dimensional submanifold of the 2n plus 1 sphere is called special Legendrian of phase e to the I theta if its cone is special Lagrangian of phase e to the I theta. This is again equivalent to being semi-calibrated by a nice semi-calibration. And there are also these additional characterizations, which are quite nice. So it turns out that being special Legendrian of some phase is equivalent to being minimal and Legendrian. So Legendrian meaning that the contact form vanishes. Being special Legendrian of phase plus or minus 1 is equivalent to being Legendrian and the imaginary part of psi vanishing. So again, you can study these things, and certainly people have, especially in low dimensions. Their deformation theory has been studied, for example, and people have studied their Morse index. The other relevant aspect of the 2n plus 1 sphere that's incredibly important is, of course, the Hopf vibration. So remember, we have this Hopf S1 action on the odd dimensional spheres. This action gives us the Hopf vibration, of course, down to CPN with its Fubini-Studi metric. This is a Riemannian submersion. And well, it turns out that these nice submanifolds in odd dimensional spheres have counterparts down in CPN. So somehow there's this back and forth between submanifold theory and CPN, submanifold theory in odd dimensional spheres, and then these cones in CN plus 1. So for instance, if you have a submanifold N in CPN, then its preimage under P is CR if and only if that submanifold is complex. Moreover, a submanifold, just sort of more generally, really, there's a local statement. If L is a submanifold in the odd dimensional sphere, then it's CR if and only if it's locally of that form. And finally, if sigma is special Legendrian of some phase, then its projection down to the CPN is minimal Lagrangian. I suspect that there's some sort of converse to this, but I can't quite find it in the literature and haven't sat down to prove it. But I suspect that this last bullet point can be, strengthened somehow. But yeah, so the upshot is that sort of, anytime you have a result about one of these sorts of submanifolds in CPN, you should immediately ask whether I can get some sort of, whether I can, that gives me something about a result in about minimal submanifolds in odd dimensional spheres and vice versa. Anyway, all of these submanifolds I think are interesting already in the lowest dimension of the 5 sphere. Already in the 5 sphere, there's quite a lot to say. Moreover, the 5 sphere has the nice property that it's related to the 6 sphere. So many of the submanifolds in this part of the talk are actually related to the ones mentioned earlier. So let me explain how. If L is a 3-dimensional submanifold in S5, and I'm thinking of S5 as the equator in S6, then it turns out that L is CR if and only if it's Lagrangian. So CR threefolds in the 5-sphere give, in a sense, I hesitate to say trivial, but simple examples of Lagrangians in S6. Similarly, if I have a surface, a 2-dimensional surface in S5 that's special Legendrian, that automatically gives me a holomorphic curve in S6. And in fact, all holomorphic curves in S6 that lie in an equatorial S5 arise in this way. And this is equivalent to the sine cone being Lagrangian. So this is sort of a kind of a funny relationship between holomorphic curves and Lagrangians in the 6th sphere. You can, take the sine cone of a holomorphic curve and get a Lagrangian, a singular Lagrangian that way. Okay. All right, so let's play the same game. What can you say about the Morse index of these things, about the homogeneous ones at least? So let's let L be a compact CR threefold. Then by Mashimo's result from earlier, the homogeneous ones, well, there's only 2 of them up to congruence. There's the equator and there's this Varonese RP3. The Morse indices have been computed. They're 2 and 8 respectively. And I personally would be interested in knowing whether the Varonese RP3 has lowest Morse index among all compact embedded CR threefolds that are not totally geodesic, of course. So if I have a compact embedded CR threefold, that's not the totally geodesic, that's not the equatorial S3. Is it true that the index is at least 8 with equality if and only if L is congruent to the Varonese RP3? Maybe someone has done this, but I haven't seen it. So I don't want to say it's open necessarily, but maybe it's in some paper that I missed. And again, you can play this game for special Legendrians. Here, it's maybe a bit more tractable because special Legendrians in S5 are surfaces, so they're amenable to complex analysis, for instance. Special Legendrians are also maybe a bit nicer in other respects. The homogeneous ones are simply the equator and the equilateral torus. The Morse indices have been computed by Simons and Urbano. And Urbano, just for illustration, proved the style of result that I was sort of hoping for in the CR setting for CR threefolds. So if you have a compact orientable special Legendrian in S5, not the equator, then indeed the index is at least 8 with equality if and only if your surface is congruent to the equilateral torus. And the same thing, same sort of result is true for the nullity. Right. So these sorts of characterizations I think are very interesting, and you can sort of play this game systematically for the submanifolds of the 6th sphere, the 5 sphere, etc. I think it would be nice to sort of see this all worked out. It would give us sort of a measure, sort of some a way of taming all of this chaos of the sort of submanifolds. Another direction, sort of switching gears slightly, related to minimal submanifolds and spheres are these so-called Berger spheres, which have received some attention lately. So recall again, one more time, this Hopf vibration, which I'm denoting by P. The 2n+1 sphere is this S1 bundle over CPN. You can take the S1 fibers and you can squash them by a factor of tau. Tau is positive. And in doing so, you get these so-called Berger spheres. Okay, so these Berger spheres are homogeneous Riemannian manifolds. Okay, so I'm going to denote them following Toralbo and Urbano by S2n+1 sub tau. So this is the 2n+1 sphere, but now I have this metric here. Notice that if tau is 1, I get the, well, it's supposed to be the round metric I get back. Right, so geometrically what's happening is the Hopf vibration for this new metric continues to be a Riemannian submersion, but now the fibers have length 2 pi tau. So you can imagine sort of squashing them to 0. Just a fun fact is that, this might seem like a, sort of a strange construction, where would you ever see Berger spheres, quote unquote, in real life? It turns out that Berger spheres arise very naturally. They are distance spheres in CPN+1. So if you're in CPN+1 and you're doing, actual kind of geometry with measurements and distance spheres and such, sort of the Berger spheres are right there. There's sort of no avoiding them. They really are very fundamental. So a question you might have is, what are the simplest submanifolds of the Berger spheres? And here I mean something different by simplest. Here I mean totally geodesic. Surprisingly, the classification of totally geodesic submanifolds in the Berger spheres is relatively recent. This is a result of Toralbo and Urbano. And what they show is that if you have an immersion of a surface of dimension at least 2, and here the squashing factor is strictly less than 1, then that immersion is totally geodesic if and only if the image is up to congruence an open subset of one of these things. Either it's sort of this D sphere here, and D is at most N, or it's sort of a Berger subsphere. And I suppose this has been open for quite a while because in general, this Berger space or the Berger sphere rather, I should say it's a homogeneous space, and in general, classifying the totally geodesic submanifolds of an sort of some arbitrary homogeneous space is not necessarily so easy. This is related to the following result that they prove. So again, when tau is 1, we're dealing with the sort of standard round 2n+1 sphere, in which case, by Simons's theorem, there are no stable minimal submanifolds. But you might wonder if as tau shrinks, as you squash, maybe stable submanifolds will suddenly appear. And in fact, that is exactly what happens, where the dimension of the minimal submanifolds that appear depends on the squashing factor. So if tau is strictly bigger than this number, then there are no compact, stable, immersed submanifolds of dimension D. But when you're at this critical threshold, it turns out that there are stable minimal submanifolds, and they are precisely these. They're the pre-images under the Hopf vibration of complex submanifolds. And there's this dimension restriction. And moreover, when tau is below this threshold, then what you can say, or what Toralbo and Urbano were able to say, is that they have a slightly more general statement than this. Again, these submanifolds are all stable. So somehow they become stable beyond this threshold. But the point that I really want to make here is that these submanifolds are not random, right? I mean, this sort of this pre-image of a complex submanifold, these are all CR, right? These are semi-calibrated, right? So this is somehow another instance of this sort of philosophy that somehow different measures of simplicity for submanifolds kind of have a funny habit of coinciding, right? Okay, so the 4n+3 sphere is fairly formidable. Of course, it is itself an odd dimensional sphere, but now the amount of structure that you have is somewhat overwhelming. And so in the last part of this talk, I just kind of want to comment very, very briefly on aspects of the 4n+3 sphere that I think are worth highlighting. So the 4n+3 spheres are indeed quite special. So first of all, from the point of view of homogeneous spaces, for example, they're homogeneous spaces in several different ways. There are many different, compact Lie groups which act transitively upon them, right? The special orthogonal, special unitary, symplectic groups, etc. There's quite a few, which is very different from the other spheres. But not only that, being odd dimensional spheres, they admit complex Hopf vibrations down to projective space, down to CP odd. But now there's not just one such complex Hopf vibration, there's actually a 2 spheres worth. There are actually sort of a 2 spheres worth of complex Hopf vibrations, which ends up being very important, that there's this family of them. But not only are there the complex Hopf vibrations, there's the quaternionic Hopf vibration, which is an S3 vibration. I'm going to call it H. And these two are related. You can sort of factor them by means of this twister S2 vibration called tau for twister. So you can summarize the story in what Boyer and Golitsky call the diamond diagram, because they have this picture slightly rotated, and then the way that they draw this picture is in the shape of a diamond, but I like it this way. So here's S4n+3. It's the unit sphere here in R4n+4. You have these family of complex Hopf vibrations down here, the twistor vibration here, and these two together factor the quaternionic Hopf vibration, which is an S3 vibration down to HPN. Okay, so this is called the diamond diagram. It's the simplest instance of well, more complicated diamond diagrams. So, all right. So now that we have this quaternionic Hopf vibration, what can we do with it? Well, in the spirit of analogy, which is the sort of idea, the principle of this talk, sort of analogies, we might ask to try to formulate and prove analogs of Tiralbo and Urbano's results in the quaternionic Berger spheres. This is probably possible. I have not done this. I've certainly, folks have asked me about this kind of thing, and I've had brief conversations. It seems that there's a fair bit of interest in doing this. And I suspect that this is possible. Maybe you can get an analog of Tiralbo and Urbano's result in the, using this squashing, where you squash the 3 spheres instead of the circles. But I think this comes with some warnings. I think, oftentimes when you, sort of take a result in the complex setting and you try to go to the quaternionic setting, sometimes it's straightforward. Sometimes you take a result in CPN, you move to HPN, and everything works just fine. But here I wonder just how straightforward this might be. And this is for 2 reasons why such a generalization might not be so straightforward. So first of all, it turns out that there are quite a lot of totally geodesic submanifolds in these S3 squashed 4n plus 3 spheres. And by a lot, well, I'll show you what I mean on the next slide, but there's quite a lot. And that means that somehow it's just somehow very complicated. These S3 squashings of the 4n plus 3 spheres are somehow just considerably more difficult. I mean, just from the point of view of how many totally geodesic submanifolds there are. And not only that, there are just thousands and millions of nice semi-calibrations on the 4n plus 3 spheres, which is a beautiful thing, but it's also a bit overwhelming. The point here is that the semi-calibrated submanifolds in 4n plus 3 spheres, these are reasonable candidates for, I think, in my opinion, for what could be the stable submanifolds in the squashed 4n plus 3 spheres. That is at least what we saw in the 2n plus 1 sphere case, where the CR submanifolds were the stable ones after you squashed by a sufficient factor. So let me show you what I mean by a lot of totally geodesic submanifolds. This is a recent result of Olmos and Rodriguez-Vasquez. They classified the totally geodesic submanifolds in the S3 squashed 4n plus 3 spheres, and well, this is what they get. Yeah, it's quite a list. The list depends on tau, depends on n, and it's quite formidable. Yeah, it's fairly surprising, I think, actually, just how involved it is. As for the semi-calibrations, I won't go into this, but this is sort of just a further advertisement for the Bryant Harvey paper. So last lecture, I pointed out that, I remarked that there are hyperkähler manifolds, including Euclidean space. Here, Euclidean space is a trivial flat hyperkähler manifold. There are infinitely many natural calibrations. You can take suitable polynomials of the 3 Kähler forms, right? There's these 3 Kähler forms, omega I, omega j, and omega k. You can take suitable polynomials of these. Bryant and Harvey explain how in degree 4. And you can get just tons of calibrations. And from the philosophy that we've discussed earlier, this gives you lots of nice semi-calibrations on the 4n plus 3 sphere. Okay, so in closing, I just want to say 1 or 2 more things. So among all of these sort of millions of nice semi-calibrated submanifolds of the 4n plus 3 sphere, are there any that stand out? Are there any sort of distinguished ones, any that you would sort of recommend as being the best? Wading through all the semi-calibrations, I would say my candidate would be the so-called CR Legendrians, which I think are good candidates for possibly a lot of index style and stability style results, possibly. So here's how this works. Take R4n plus 4, equip it with its standard hyperkähler structure. So you have the flat metric ijk and the corresponding Kähler forms omega I, omega j, omega k. A 2n plus 2 dimensional submanifold is called I-complex Lagrangian if it is simultaneously complex with respect to I, Lagrangian with respect to omega j, and Lagrangian with respect to omega k. So this is surprisingly possible, which is a bit funny because, you know, complex submanifolds are often treated as somehow the opposite of Lagrangians, but of course that's for a given structure. Here we have, you know, a type of submanifold which is somehow simultaneously Lagrangian and complex. Of course, that's possible because the structures are different. But these things do exist, which is quite remarkable, and they're studied more often by algebraic geometers than by differential geometers. And so some fun facts are that any two of these imply the third. And moreover, complex Lagrangians are in fact special Lagrangian. Excuse me, for omega j and omega k. Here I'm being a bit vague. You have to also specify which complex volume form you mean. And that does matter because the phase is actually very particular here. But let me not go into that. The point is that these form a very you know, beautiful and distinguished subclass of the special Lagrangians that are perhaps more tractable for certain problems in special Lagrangian geometry, maybe. And again, just sort of, you know, remarkable that these submanifolds are simultaneously calibrated, you know, in sort of three different ways. They're complex and special Lagrangian twice. Okay, so do complex Lagrangian cones exist? They do. There are complex Lagrangian cones and non-trivial complex Lagrangian cones in Euclidean space. And their links, I have to call the link something. And so I'll say that the link of such a thing is called ICR Legendrian. And I would argue at least that these are among the best minimal submanifolds in 4n plus 3 spheres. And it's likely that they, you know, will show up here and there in various index characterizations and further studies going forward. Anyway, yeah, so in closing, I'll just say that, you know, one of the morals here is that there are different, there's various submanifold geometries in the 4n plus 3 sphere, various submanifold geometries in our 4n plus 4, as well as in CP odd and HPN. And you might hope that these various submanifold geometries are related to each other in some way. I won't rehash how all this works. But you can, in fact, develop sort of a dictionary between the various submanifold geometries in these four spaces. This is what was done in a recent paper with Ben Aslan and Spiro Karijanis and myself, sort of you know, going back and forth between these various spaces so that, you know, the relationships are all clear. All right, well, that's all I wanted to say for today. So thanks for your attention.
All right, thank you very much. Any questions? All right, thanks very much for these set of nice examples.